They'll be put out this afternoon along with directions. Please try to fill in the directions, follow the directions and filling them in, otherwise we'll have to go back and forth to get them filled out correctly before we get you reimbursed. You will need to keep your airline ticket at the back of it if you are getting reimbursed for airline travel. And what we suggest doing is you're going to need to send us the original, but you should keep a copy, a Xerox of it, just in case the original gets lost in the mail. Okay, next. On Saturday night, there won't be a hospitality suite. Instead, from 7 to 9 in Metcalf Hall, which is the second floor of the Student Union, which is 775 Commonwealth Avenue. It's right over the bridge, essentially, in the direction of the math department. We'll have a sort of a reception. There'll be hors d'oeuvres and punch and a cash bar. Third, the T-shirts are closing, so to speak, at noon. So get your orders in right after the talk. For those who don't know, the T-shirt, some people have it. It's a proof of Fermat that will probably fit on the margin. Modulo, a couple of bibliographical references. Anyway, and the fourth announcement is tonight we're not going to have beer. We will have light refreshments. Instead, we'll have Tuscany's ice cream starting at 8. So anyway. And for those who don't know, that's in the hospitality suite. If you aren't in the dormitory and you're registered to the conference, then you should have been given a little red card that will let you get into Rich Hall. Because without a little card, they won't let you in. So if you've lost your red card and you're registered to see somebody at the front desk, you get another little red card.
I just wanted to make one more announcement, and that is that there's been a lot of questions between talks and after talks about the mathematical content. And there have also been some people who volunteered to help answer questions. And so we were thinking about maybe trying to organize a question and answer session in the dormitories informally in the evenings. And so starting tonight, you might just look around. You'll probably see signs up. We're going to move blackboards over. There are various graduate students from the area in Princeton who've been studying these things for a long time, and they know a lot of the stuff, and they would enjoy talking to people who have questions. And so if you happen to look for this place someplace tonight, it will probably be happening every night. So that might be something to do in the evening.
Great.
Very nice.
Sorry, one more. Logistics get very complicated around here. We need to see all the speakers after the talk up front for various reasons. So anyone who's giving not a 20-minute talk, but one of the hour talks, so they could just congregate in front after various talk, that would be great, because I have some logistical things I have to pick up with them. Thanks.
So, okay, thanks. I was asked by the organizers to give a few lectures explaining a little bit about the deformation theory of Galois representations, leading up to a certain specific theorem, which I hope that I'll do in some way or other. But what I want to do is make this as useful and friendly to the audience as possible. And one way of doing it is to suggest that anybody who's interested in a very, helpful, I think, annotated bibliography to the entire literature about deformations, not only Galois representations, but deformations before that in algebraic geometry. And it's an annotated bibliography in the sense that there's a certain amount of chat about each item or many of the items on it. You can get it by, it's compiled by Chuck Doran. And now he gave me instructions about what you're supposed to type in after the cursor sign to get it by anonymous FTP, but people interested, come to me at the end of the talk, and I will try to work this out with you. Okay, so I want to begin sort of reminding people of the sort of general picture. Much of this one you've seen in previous lectures already. I don't think I'll be violating any notational convention by letting Q be the rational numbers. And I'll let Q bar be a choice of algebraic closure. And I want to take for S for me will denote any finite set of primes, of prime numbers if you want. I'd like to consider the intermediate field in Q bar, which is the maximal algebraic, of course, extension in Q bar, which is unramified outside S. So let's have some notation for, we have notation for this Galois group, but let's have some notation for this Galois group. It's a Galois extension. And we'll call it G. Q is the field, and S is the set of allowed ramified places. Now, what sort of a group is it? Well, of course, it's a profinite group. In fact, one can write it as the limit of finite Galois extensions. So overall, of the Galois extensions of K over Q, where K is finite, Galois, of course, and unramified outside S, another way of saying that is the discriminant of K over Q is divisible only by primes occurring in S. Okay, each of these is finite, and it's a limit. It's a projective limit, so it's a profinite group, profinite topological group. And it has appeared in, possibly not in this notation, but it has appeared in principle in a lot of the talks that we've had and will continue to appear.
Could you write a little larger?
Oh, sure, yeah. So there's of course a local theory, so we can take QL to be the L-adics, an L-adic extension, the L-adic numbers, and we can take the algebraic closure of QL. And the notation that people have used for the Galois group of the algebraic closure of QL over QL has been GL. And GL, of course, is also a profinite topological group. The connection between GL and the local and the global comes from making a choice of an embedding of Q bar and QL bar. Of course, the minute you make such a choice of embedding, you get a continuous mapping of GL to the Galois group GQS. But this mapping, of course, depends upon the choice of the embedding, and if you change the embedding, this mapping will change up to conjugation. So this is a well-defined continuous mapping, but defined up to conjugation, dependent upon the embedding. You change the choice, you change the mapping by conjugation. Okay, what really sorts of groups are these? Well, it's well known that this one is at least topologically finitely generated. Topologically, oh gosh, I should write larger, but I will from now on. Finitely generated. So this guy is okay. Now, one of the deep secrets, dark secrets about this is that I don't think anybody knows. In fact, I don't know whether anybody has a bet as to whether this is topologically finitely generated or not. And so if we're going to treat these in some reasonable way, we need to come to grips with this. And the way I want to do that is by mentioning that both of these groups satisfy a certain finiteness condition which is slightly weaker, or perhaps somewhat weaker, than finite generation. So let me say that any, oh, okay, now large. Any profinite group will satisfies I'll call it the p-finiteness condition. Where p is some prime number. If for all subgroups which are open of finite index, so open subgroups of finite index, these will of course also be profinite groups. There are only a finite number of continuous homomorphisms of that subgroup to Z mod p. So one way of saying that is the set of homomorphisms continuous, of course, from pi naught to Z mod p is finite. There are various other ways of saying that. And it's known that both of these groups, of course, this one, it follows from finitely generatedness, but both of these groups satisfy the p-finiteness condition for all satisfy p-finiteness for all p. Okay. What sort of a mapping is this? Well, what we can do is we can sort of introduce the notation for the analysis of the local group. There's the inertia group, which is a normal at L, which is the normal subgroup of GL. And the quotient of the group GL by the inertia, this is inertia at L, is isomorphic to the Galois group of an appropriate choice of algebraic closure of FL and this, as is well known, is as a profinite topological group just the profinite completion of the integers. And in fact, if you make the right choice, you can get the integer 1 to correspond under this isomorphism to what I think Joe Silverman called sigma L Frobenius, which is defined by the equation x goes to x to the L in FL bar. Okay, here we go. Now, we can analyze this map, GL to GQS, in two cases, namely when L is not an S. Then the mapping from GL to GQS factors through the quotient by the inertia group. The inertia maps trivially to GQS, which is, of course, by the above isomorphic Z hat, and we can take the image of the identity here to be some element in here, which we'll call Frobenius in GQS. I don't know whether I want to call it sigma L again, so I won't, so I'll call it phi L. And of course, this element is as well defined as this map, which is well defined only up to conjugation. And so it really defines not an element so much as a conjugacy class. And this is the L Frobenius conjugacy class. So for L naught and S, what we have really is a kind of package. Namely, we have the group GQS itself as a profinite group. And for every L naught and S, we have a chosen conjugacy class in it. And as is sort of well known, one of the sort of principal targets for number theory is to get some understanding, to try to study this, not only the profinite group GQS, but the package. Well, what's known up to this point is certainly we are pretty good when we abelianize this. Let us say pass to the abelian package if we take GQS and replace it by its quotient, maximal abelian quotient, dividing by the appropriate commutator subgroup. And of course, once we do that, each of these conjugacy classes specializes to a single element. It's well defined now as an element, which I might call phi Lab for L naught and S. And one of the great glories of number theory is that we have, well, if you're a number theorist and you want to cheer yourself up, you can say we completely understand this. That is to say, we can construct, by class field theory, we have a sort of an absolutely elegant and complete construction of this package, if you wish. Of course, if you want to pull yourself down a peg, you can say, even here, we're not all the way home. We don't know Leopold's conjecture, for example. But, of course, we might want to try to construct this package. And in order to do that, we have to face another dark secret about GQS, which is it's not even well defined. It's well defined only up to a choice of algebraic closure. And so GQS is really only, it's well defined up to conjugation. And it's a very sort of difficult thing to imagine to be able to produce by some canonical construction, a group which is known only up to conjugation. But there is an approach, sort of dating from at least 30 years ago, called the Tanakian approach, which deals with such matters. The obvious thing to do is to try to understand not the group itself, but its representations. Perhaps representations into some linear group like GLN. Understand its. And of course, these have appeared profusely in the previous lectures and will continue to for n equals 2. Okay, understand these representations. I distinctly didn't say JLN of what, because we have to sort of think a bit of what's the appropriate receptor here that would sort of collect the maximum amount of information we might imagine to collect from such a Tanakian approach. And of course, what we're going to do is take GLN of certain rings. So what sort of rings should we put in here? Now, the key here is to think of this and realize that this is a profinite group. And so what we'd like to do is have rings where this is as tight a fit as that as possible. Let us say we'd like this to be a profinite group as well. And so from now on in our lectures, by a coefficient ring, this is going to be a definition. A will be the letter. Will mean a commutative local Noetherian ring. The residue field I'm always going to call little k here. And I'm going to always assume finite. And P, by the way, will be its characteristic. So such a thing is already a profinite topological ring. If MA is its maximal ideal, it can be written as the projective limit of A modulo MA to the nu. As nu goes to infinity, each of these is finite surjective maps. So it's a profinite topological ring. And we can take GLN of A, alias the units in the n by n matrix algebra of A, and we can endow this with its natural topology. It gets its topology by being viewed as the limit again of GLN of A mod MA to the nu. Of course, each of these is finite groups. Each one maps surjectively to the next. And so this is, again, profinite. So the type of representations I will be considering are continuous representations into GLN of some coefficient ring A. Now, well, let me stop this here. Now, whenever I have such, I also have a sort of a natural rock bottom projection. Namely, I can replace A by, I can reduce A modulo its maximal ideal to project GLN of A to GLN of the residue field K. There's a nice surjection. And generally, if this representation is called rho, I will tend to call the reduction modulo the maximal ideal to GLN of K rho bar, and rho bar I'll call the residual representation attached to rho. Now, there are various ways of viewing this. I can either think of it as a representation into GLN of A, or there's an algebraic approach as well. And so for that, let's sort of start with an arbitrary profinite group, profinite topological group, and an arbitrary continuous representation into GLN of one of these coefficient rings A. And then here, of course, will be its residual representation. On the other hand, I might want to take a matrix algebra approach to this. And one way of doing that is let's build the group algebra completion of the group pi over the ring A. So I'll call A double brackets pi just the limit, the projective limit of the group rings A brackets pi mod pi 0, where pi 0 ranges through all normal open subgroups of finite index. And there's a natural topology on each of these, and it's a profinite ring. It's a profinite A algebra. Now, any continuous representation extends rather naturally, completely naturally, in fact, completely determines a representation of A algebras into the full matrix group Mn of A, similarly continuous. Of course, I could similarly pass to the residual representation attached by dividing A by its maximal ideal. Now, if you think about it for a few seconds or minutes, you see that it's really a one-to-one correspondence here. Natural one-to-one correspondence, you can either think of the representations from the group pi or the algebra representations. Why? Well, of course, R will restrict to pi, and pi consists in only units in this ring, so we'll map to the units there. And any representation extends essentially by linearity to a representation R. Okay, I want to start with a proposition. Call it proposition 1. Which, by the way, I'm going to give 3 propositions, and this is a treatment which is due, a lot of the results were sort of known quite generally or sort of elsewhere, but this particular treatment is due first to Carriol and then extended by Serre. Proposition 1 is very well known. Proposition 1 says that rho bar is absolutely irreducible. Absolutely irreducible, of course, means that even if you extend the little field K, see, rho bar is just a representation in the usual sense into GLN of a field, and even if I extend the little field K to its algebraic closure, it remains irreducible in the sense of linear representation theory. If and only if R, the corresponding R, is surjective. And the proof? Well, step 1 is quite easy because I'm going to refer to the literature, namely, step 1 is when A is a field itself. So it's like saying that rho bar is absolutely irreducible if and only if R bar is surjective. And that's standard, and in the notes there's a reference to Bourbaki, which does it. Step 2, well, I have to show that if R bar is surjective, then R is surjective and conversely, and that's Nakayama's lemma. Okay. There's a corollary already of this. Corollary which in this context should be called Schur's lemma. Namely, suppose we have, so let rho from pi to GLN of A is any coefficient ring, of course, be residually absolutely irreducible. What does that mean? That means its residual representation is absolutely irreducible. Then any matrix, call it M, in Mn of A, which commutes with every element in the image of pi, is scalar. Proof is if rho bar is residually absolutely irreducible, then by proposition 1, its corresponding R is surjective. Now, any matrix in the image of pi which commutes with, any matrix in Mn of A which commutes with everything in the image of pi commutes with everything in the image of A double brackets pi. But R is surjective. So our matrix M, so step 1 if you want, is our matrix M commutes with, is in the center, I'll just say, is in the center. Because it commutes with every element, any guy in the image of R, and R is surjective. And the center of Mn of A is just the scalar matrix, matrices A times I n, where I n is the identity matrix n by n. That last thing is completely, for any ring A, you can do it as an exercise using. It's completely elementary. So that's step 2. Okay. Proposition 2 which is the second in our series of 3. And the point of the proposition I want to say is that the point of it is that these representations into GLN of A's, where A is any coefficient ring, they're not as scary as you might think. They're, in some sense, as amenable to character theory as the classical theory, provided, of course, the representation is absolutely irreducible. So is residually absolutely irreducible. So the same hypotheses. Let rho to GLN of A be a representation of any pi, which is be residually absolutely irreducible, meaning its rho bar is absolutely irreducible. Let rho prime be any representation. Same GLN, same A, same pi. Be any representation. Representation means continuous, of course. Now I make a hypothesis. Okay, here we go. How's that? The hypothesis will be that the traces of the characters, if you wish, of rho and rho prime are equal. Suppose that oops. No, what am I doing? Ah, that's what I'm doing. Suppose that the traces, but this trace to A, maybe I should keep that proposition a little more. Oh, where are we? Oh, I see. This, okay. Of rho of any element, that's the character function for the representation rho, is equal to the trace of rho prime, G, for all G and pi. Conclusion. Rho is equivalent to rho prime, and the equivalence is conjugate. It's as conjugate in the evident sense, that is to say, these guys are intertwined by an element of GLNA. Okay, here I won't give quite the proof. I'll give you a sketch. It's kind of neat. In the notes, there's a bit more detail. Okay, step one. Step one, again, is let's take A to be K. So we're in classical representation theory of fields. It's almost, this would be immediate then by sort of the standard theorem of character theory if K were a field of characteristics 0, but K is not. It's a finite field. It's still dual. It's still part of the sort of standard linear representation theory by virtue of the fact that rho, if A is K, is residually absolutely irreducible. That is to say, it's absolutely irreducible. So noting is absolutely irreducible by hypothesis. And again, the notes has a sort of a standard Bourbaki reference for this. The fun is in the sort of slightly, in the later steps, so to speak, of this proof. Step 2 is, since a rho prime is equivalent, well, so that means we get rho bar, the residual representation attached to rho is always equivalent to rho bar prime. Now, step 2 is we're going to forget this information. We're just going to remember that a rho bar prime is also then absolutely irreducible from step 1. And we want to introduce the algebra versions of the rho and rho prime. That is, say, I'll call them R and R prime. So we have R and R prime, which are A algebra, continuous A algebra homomorphisms from A double brackets pi to the matrix ring rather than the GLN, rather than its units. And by proposition 1, since the residual representations attached to R and R prime, or rho and rho prime, are absolutely irreducible, we have that they're both surjective. Now this puts us in a situation where we can apply what Sayre calls Goursat's lemma. And Goursat's lemma does something quite general, but in this particular instance, I'm just going to write out what it wants to do. We take A double brackets pi, and we're going to combine the R and R prime in a pair of maps, R, R prime, to the product of the matrix algebra with itself. And the important, so we get, of course, a mapping. And the important hypothesis here is that both projections here are surjective. Now, I want to consider the image as a sort of submodule, subalgebra of MNA cross MNA. And what Goursat's lemma does it characterizes this image. And I'll just tell you exactly the characterization you get straight from Goursat's lemma we'll be using properties of MNA, but it implies the following. It implies that there exist two things. There's an ideal in A. That's unique, by the way. And an element in GLNA, which is not unique, in fact, such that we can write phi in this fairly simple form. It's the set of couples, alpha and alpha prime, in MNA cross MNA, which have the property that alpha prime is essentially intertwined, alpha and alpha prime are intertwined by gamma, at least modulo I. So I'll write it that way. Gamma alpha prime, maybe alpha inverse, is congruent to alpha prime modulo I. And the quotes around modulo I means I want this equation to be an equation which holds true in Mn of A mod I. That's the only sense in which that would, so i.e. in here. Okay. Well, if that's the case, and I don't want to erase this, well, I'll erase it and I'll remind ourselves of it. If that's the case, what I want to do is I want to, I'll be done, is if I can show that I is the zero ideal. Because I is the zero ideal, what does that mean? That means that R and R prime are intertwined by an element gamma in GLN A mod 0, GLN A. So that's what my proposition is really saying. So let's tease out this consequence from our hypotheses. Namely, let's take an element x in I, and let's build a pair, alpha alpha prime, which by this construction has to lie in phi. So I'll let alpha be a matrix which has 0 in all coordinates except the 1, 1 coordinate. So x and 0s elsewhere. And I'll take alpha prime to be just the 0 matrix. And if you think of it, by this description, alpha and alpha comma alpha prime really live in phi. Because modulo I, both alpha and alpha prime are 0. And of course, any gamma will intertwine 0 with 0. But if that's the case, and if you consider the fact that the trace of R is equal to the trace of R prime, we immediately get, just by the definition of phi and the fact that the traces of R and R prime are equal, that the trace of alpha is equal to the trace of alpha prime. But the trace of alpha is x, and the trace of alpha prime is 0. Okay. As a corollary, which I will just state in the form in which it will be it's particularly relevant to us, if you wish. I'm going to replace pi by GQS. And if I let rho and rho prime be two representations of GQS into GLN of A, and I require that one of them, say rho, is residually absolutely irreducible. And I ask that the trace that for L primes not in S, the trace to A of rho of the Frobenius element phi L is equal to the trace of rho prime of the Frobenius element phi L. And if I ask this for all L not in S, then the conclusion is that rho is equivalent to rho prime, and in the strict sense that it's intertwined by an element in GLNA. Of course, I could even be more sort of weaken the hypothesis. I can ask for all L avoiding any set of Dirichlet density 0. And this is by Chebotarov. Now there's a third proposition in this series, which is also quite useful. And this proposition I won't even, I've forgotten what I've even, yeah, I gave a fairly elaborate sketch in the notes, but I won't give any proof of. We'll call it the descent proposition. Proposition 3. The same hypothesis, let pi be any profinite group and rho be any representation into GLN of A, where rho is residually absolutely irreducible. And now let's suppose that we have another coefficient ring, A0, another coefficient ring, residue field same case, same field, or it doesn't have to be actually any residue field, but I will keep it this way. Actually, maybe I shouldn't. I don't need it. Contained in A, such that all the traces of elements, the character function of rho, takes values known in A but A0. So the trace of rho of all elements to A, which of course would lie in A, actually lies in the subring A0. Well then, this statement is you can actually descend the representation to GLN of A0. That is to say, then there is representation, which I'll call rho 0, to GLN of A0. And let me just say descending row. Meaning, of course, that if I extend the scalars from A0 to A to get a representation of the GLN of A, and I consider the induced representation for rho 0, I get something which is equivalent to rho. Okay, the point of sort of stating these three propositions and giving at least some hints of proofs is to indicate how accessible they are, and they should be, in some sense, part of the general linear algebra of representation theory. Okay. I now want to begin the deformation theory in earnest, and to do that, I'll sort of give at least a list of the type of terms I want to introduce. So this is a vocabulary list. So I want to talk about strict equivalence, deformations, universal deformations, and representability in general, and then two notions I'll call the first nearly representable things and relatively representable things. So that's what we're in for. It'll be more painless than you think, I think. But, okay. So let's suppose that I have pi a profinite group and a mapping of coefficient rings. Homomorphism. Of course, homomorphism of coefficient rings means these, I want them to be coefficient rings with residue field K, same field. And I'll want the homomorphism to be to induce the identity on the residue field. Inducing okay. Now let's suppose we start out with a representation from pi to GLN A0. We can imagine trying to lift it to GLN A1, where the mapping here is induced from our homomorphism of coefficient ring. In fact, we can imagine trying to lift it in many ways. So let's try to lift it in two ways. I'll call them first lifting rho, and the second one rho prime. And we'll say that we're assuming they're both liftings. That is to say, each rho and rho prime make a commutative diagram here. And I'll say that rho prime is strictly equivalent to a rho. And this is a notion relative to rho 0, rho 0. If they can be intertwined, but if they can be intertwined by an element of a specific sort. So let's introduce the kernel of this map. So let's let gamma in here be the kernel of this map. So if rho prime is intertwined by an element, rho prime and rho are conjugate, and that conjugation is by an element of the kernel. Okay. Now the most important rho 0 for us will be the residual representation of some representation. So let's sort of consider that situation. So let's suppose we have pi and I'll call it rho bar into glnk, a representation. And suppose I have a coefficient ring, any coefficient ring with residue field k, so I can reduce my the maximal ideal and I get my k. And I can consider various liftings to gln of a. In fact, I can consider a strict equivalence class of liftings. So by definition, a deformation of rho bar to the coefficient a is precisely that. It's not one lifting, but a strict equivalence class. Strict equivalence class of liftings of rho bar to A. Well, I should really say to gln A. Okay, the theorem that I think Henrik Lenstra is going to prove in one form in the next lecture is the following. Let rho bar be some representation. And we want a hypothesis about both pi and rho bar. The hypothesis about pi is that it satisfies the p finiteness condition in the beginning. So a replacement of topological finitely generatedness. And the hypothesis on rho bar is that it be absolutely irreducible. Then there is a coefficient ring. I could call it R. It's uniquely defined by this situation, so it's uniquely defined by rho bar up to a unique isomorphism. And a deformation it's the universal deformation, so I'll call it rho universal. Well, rho with the universal up there. I'm not going to use that too much. To gln R. And it's a deformation of rho bar. Of rho bar to R, which is universal in the evident sense, that is to say, such that every deformation of rho bar to any coefficient ring whatsoever of residue field K is obtained from the universal representation by a unique homomorphism of rings, which is universal. And by the way, I'll also give a slightly functorial, slightly more category theoretic definition of universality, which will play a role a little later, in the sense, in the evident sense, that given any deformation of rho bar to any coefficient ring A, let's call that deformation rho, rho is obtained from rho universal by a unique homomorphism of coefficient rings. And obtained, of course, means that we have our universal representation going into GLN of the universal ring, and we have our deformation class going into GLNA, and there's a unique homomorphism from R to A, which when we induce the homomorphism on GLN level, we get a commutative diagram. Okay, that's sort of the more sort of direct way of describing what it means to be a solution of a universal problem. If it is a solution of a universal problem, it's, of course, easy to see, and it's a nice exercise that this R of rho, if there is such a ring that satisfies this condition, it's unique up to unique isomorphism. A slightly more functorial way of thinking of it is if we define the set of deformations to a coefficient ring. So if I let d rho bar of a coefficient ring A to be just the set of rho bar to A. It's a set. So what is d rho bar? D rho bar is a mapping, if you wish, from a category, if you want, of coefficient rings with residue field K, some category, with a category of sets. It has two evident properties. It's covariant first. As a functor, it's a functor. And it also has the property, if I take the coefficient ring K itself, then d rho bar of K, well, there's only one deformation. I mean, there's nothing. I mean, so it's rho bar. So it's a singleton. So that puts this functor in the deformations in the sort of in the rather large zoo of all functors from this, the category of coefficient rings to the category of sets. It is completely determined if I restrict it to a smaller category, the category of coefficient rings which I can say which are finite or Artinian. I can put Artinian as an adjective in there, and that shrinks the category. But either with Artinian or with coefficient rings, when one says that there is a universal deformation, what one is saying categorically is the following. Just says there is a coefficient ring. Such that the functor d rho bar of any A is homomorphism of coefficient rings of R into A. And this functorial in A. Or to put it sort of much more, and it's sort of hardly more, one can restrict to the Artinian coefficient rings just as well. Except, of course, the universal coefficient ring will not be Artinian. Okay. So we will continue second hour talking about the tangent spaces of these deformation spaces, and I think Henrik Lenstra will be giving a proof of this theorem next. Is that right? Next lecture.